Hello my friend, welcome to my channel. Today we will speak about converting analog data to binary. This is special subject if you want to understand how we are converting analog data like some music data like waves. You can think like sounds waves, how we are converting to binary. So just think there's lots of points, samples. I mean, we are saying sampling, how and we just, we're just doing some quantization to put them in one place to represent them with the binary. Okay, anyway, this is the summary of it. So then we will reconstruct it, this our things, and just we can compare the original data to our new data. Okay, I mean what we created there. Okay, let's start with this title, with this caption: converting analog data to binary. Let's come here, maybe here. Let's say, right, converting, let's hide it, converting analog analog data data to binary. Okay, but let's do all of them. Maybe this one is looking like that anyway. Just take all of them into which color is red. Give me red, right? Okay, this is our title, and let's come down. We will do lots of things. We will plot there lots of graphic. I mean, some diagram to show you how to sound waves. So you can think like one place. We will say will be something like volt. Okay, this is electric signal volts. One place will represent, I mean, x coordinate will represent volts, and y coordinates will represent time, and we will check this sampling points there. Anyway, we will do all together. Just we will notate it with this way. We will visualize it with this way. Anyway, let's write there. The real world is analog. Let's do it analog. Okay, let's do it. Let's do it some different color. Maybe we do. Okay. Let's come back to here and go on black. Yes. Do it and say 0. Okay. This one is black. Black, not black. Analog, right? Then you can say, just put there anything like that. Analog, a continuous stream of varying data. Stream of varying data. Okay, this is good. Okay, let's come down and we will say now, just look around you, beyond your computer or phone, beyond your your computer. That's it. Computer or phone. There is infinity amount of visual amount of visual visual information. This one is good information. Let's say if you uh, zoom, if you zoom one part of your one part of your one part of your field, and let's say you can notice, you can notice notice, I mean, more and more details, more and more details. This is good. Let's come down and let's say now sing a little sing a little song to yourself. Yep. That's any so let's say here that's an infinite stream of that's an infinity stream of audio information. Yes, that's an so that's infinite stream of audio information. Okay, this is not n, sorry, this is n. I'm looking careful now. Let's come down and let's say your voice your voice your voice is constantly changing, right? Changing in big and in big and in big and little ways. Of course, like you can think your sound starting like something like that. Okay, your sounds, your frequency of your sounds, it's coming, growing, and just again coming down, and your sounds all the time. If you are scream like like that, then your sound is coming up and coming back again. It's just there is some balance sometime. Okay, you can think like that. Okay, let's go on again, and I will say changing in big and little ways, and microsecond by microsecond. You can think like that. Okay, microsecond by microsecond. It is with microsecond we can represent it. Okay, let's come down and say analog data is infinitely detailed. Yes, computers can only store computers can only store digital data digital data uh, infinity infinity data in binary representation. Yes, I want to give you some example here, but I don't know how to do it because I can show it you in kernel, I mean in terminal. Okay, we can do something and I can show it you, maybe like what, let's look at that. I don't have normally sounds files, but let's do it. Let's come here. Okay, we have binary and super binary files. This all about your I will show it you. Okay, so this where is it, this boot is special place for your things, Your home is exactly it in the root, okay? And our files, where is it? It's etc. This one is etc. Can think and binary. And let's this one is where we have some application here. So I'm looking for media, maybe just say media. Let's go in media and say let's go there in my file. What is that? This one is this one is a directory. Okay, let's say cat and zero in this. Oh, it's okay. If it is directory, we have to go again in it, I think. Let's go inside it. Right. What we have here, drum stack, bootware, and some information. I think it's just little lightning. I'm not seeing good information here. Python, some files here. Recycler bin. Anyway, OneDrive team music controller, right? You see music controller here. Yeah, maybe you can see from here. Let's say this one music controller and go inside it and check it. There is manage pi music controller, go inside it and and anyway we have some Python file here, but what I want to do, I just want to show it you. Anyway, I will go in binary. Let's say binary and let's come inside it. Okay, now in our place, what do you want to do? Maybe we can go in mon, this one, okay? So just think this is some sounds file, okay? Because everything in a computer file, your hard driver, SSD driver, and all of them, it is just some file, okay? It is file, not too much, not more. It is some not digital. So it's just file, okay? Let's look at that. Let's say catman. Look at that. This is binary things, okay? All of them binary information here. We can't understand it. If you understanding, you are a robot, of course. All of them, okay? Let's do C and let's come back. You can think our sounds file like that, okay? We are just so I mean computers can only store digital data, finite data in a binary representation. So you are speaking, your sounds coming in the binary numbers, okay? Then with the wires, with the circuits, all information going coming like that. You can say for that this is what code? I remember the code name as which one? Oh, I think anyway, I don't remember now. Okay, but it's all on the card motherboard, I think. Yeah. Anyway, let's go on again. Mm, so let's come little down to see better. So how can we capture? So how can we capture? How can we capture the the wondrous, the wondrous, I think it's spelling it. The wondrous, right? Analog world. I will check it. What is this wondrous? Wondrous. All right, this is good. Okay, just I check it because you want to be sure what is it. Wondrous, analog world, analog world of your sense and convert it and convert it into and convert it into digital data. Digital data. So we can capture the wondrous analog world of your sense and convert it into digital data. So this is the important point. Just think some kind of machine with electronic machine stacking MP3 media, okay, this machine. It's stacking your sounds and it's just converting binary numbers. Then computer can understand what are you saying there. Maybe computer also can give you some answer with the binary numbers, and it's coming output again with the sounds. Your input is sounds and coming inside the computer tagging it and converting binary number and stacking binary number, comparing to other things, and gives you again binary number output to making sound. This is a little crazy because to explaining, I mean, we can use process of, let's look at here, sampling, quantization, and binary, not binary encoding. This is amazing. Let's, what do you know? Let's just take this words here because this is important words, like purple maybe. Okay. Just what you have to do, you know now. Just come here, maybe here, and make line. Okay, just okay. Do this one here, and let's duplicate it. I will put also here because really they are important. Oh no, what happened? Come down. Some crazy things happening sometime. I don't know why Figma is doing that. And let's here, and really just do it long because the other side will be also there. Okay, maybe we can tag it little here. Okay, just think like that, and this one can be again there. I want to be fair for all my process. Just tag this one as there. It's okay. It's just binary encoding. It's concatenating. Okay, you can concatenate it. Let's come down and let's put here one title, subtitle. It will be subcapture. You can think and analog analog signal. Wow, we will do lots of stuff together. Okay, believe me. So we will be. What happened? Oh, let's do it blue. Right, it's amazing. Let's come down. I want to be clear here. Okay, I want to be clear words. Let's come down and really just we have to represent this place and just tag your notes. I mentioned to you all kind of this stuff have to represent with the binary numbers. I'll notice you have to be, so you have to be really clear mind to think this thing. Now we will speak about an analog signal, and we have some sample, and we will go other kind of subjects. Okay, later what we have to do. Yeah, we will speak about binary encoding, reconstruction, and we have some practice questions to make things good in our brain for memorized. Later we will go on again on. Okay. Let's come down here. Let's say, let's start with let's start with a simple analog signal waveform, a wave, uh, not like that, waveform, yes, representing signal, no, a sound, sorry, not signal, a sound. Now, this is important point. Waveform representing a sound. Like what? Like that. Let's come here. Where is our thing? Arrow. It's here. Let's do it like that. Maybe also for here we can put, well, let's come here and let's I don't know, maybe I can put here two, one more. No, it's not good here. I don't know why. Let's take it back and just I want to put more here arrow, but I don't know why it's not happening. Let's say inside, outside. Let's say inside, and maybe what, how I can do two, for a minute. What kind of stuff here? Oh no, yeah, something like that, but also this place. Yep. Okay, now it's good. Let's make it a little long. Really, I don't know normally how to do it, but just I learned with you. Okay, just tag it here. This good. And what we have to do, just tag this one again from here to this place. But I want to do arrow again. Let's come here and say arrow, and let's do it like that. This one is good. And let's say for here this is 100. Okay, maybe let's say for here 0, and for this place let's say -100. Okay, this is old stuff here. Let's take them little here to maybe 0 can be little, maybe yes, 0 can be little here or represent. Okay, and then let's put here V to represent volt. Okay, V meaning V is volt. Let's put here, and then let's also put here T, which is representing, yes, this one is representing time. Okay, this one is good here. Okay, we can represent also time. Time can be 330 seconds. We can think like that, right? Yes, we can put here to it. And then let's plot our, where is our pencil? Yeah, we can do brown maybe. Yeah, this color good, right? Let's tag it from here, and let's go up, and let's go down to make something like that, and really just do it, and just, no, this place now, wow. Let's go up and come down, and let's really do something like that, and let's say it. Let's do it. But why this place is happening? Yes. Let's come here and really just go there and just go. Okay, something like that. Okay. I'm not good to plotting good. But last I will try. I have some problem about symmetric things. So anyway, I will do crazy things now. Wait, like that. Last one is not good. Let's do it. No, maybe. Yeah. Okay. Anyway, you can think like that. Okay, we have some point here. But what is the problem here? Now, if I do something like that, then our other example will be bad. For that, I have to draw it very good. This one is that. Let's come down like that and do it. Why this place is too much going bad? Okay, let's do it little long and go up again and do it and just do it. I don't understand why. Let's do it. Okay. That's come on. Okay, this is that. I don't want to change again. I'm not. But here we have some problem. Wow. Hey, who will help me? I don't know really how to draw it because this is crazy, little difficult. It's coming from here. That's okay. And just come down to from this place to go this and again here. Okay. Let's come and go to this place. Okay, the point is here, okay? You can think really like that. It will take lots of time. I don't want to stay here. Last example, but if I use for last example, it will be bad. I don't know how to do it. Just this place will be like that and gone. Yes, and this. Okay, this is that. Really, I don't want to change again. Now I will come down. Okay, I'm so sorry really for this point because I have some problem about I have some sickness if I see things wrong. Still, I am not seeing good this image, this diagram. Just I want to be honest for this. Anyway, let's look at here. We have here the points, sampling points. Okay, between 100 and minus 100. And we have time, and we have this one as representing volt signals, and here we have waves. Okay, and now we will check what is turning here. Let's come down. Let's write things here. Let's say all analog signals are continuous, I think continuous, I think like that. Both in the time domain, both in the time domain x axis and in the amplitude amplitude and in the amplitude domain y-axis. Yes, now say that means that there is that mean uh, that means that there is a precise value for every possible value of time even as specific even as specific even as specific as 1.23455 seconds, and that value maybe as precise as precise as crazy numbers again here. Yes, look, the important points I mean here, the 1.2345 seconds, so 1.2 seconds, I mean, you can think like that. It is precise the value of that. Look at that, this volts. It will represent this volts, maybe in somewhere, okay? So we can find it, okay? But let's go on again. We are just solving things here. Now we will say our other topic, it's sampling. Yes, now we will concatenate all of our things. Let's say blue. Now the other topic is that. I told you we will speak here about sampling, quantization, and binary encoding. So this is the part of puzzle. All the things is in here. First we understand about analog signal. Now we will concatenate all of part of puzzles, all things. Let's say for that, anyway, we can go maybe till quantization. Just little long place. Okay. Let's say the first step is sampling, where we take a sample, at regular time intervals. at regular time intervals. Yes, this, I think you can see, this step reduce the steps, reduce the continuous time domain, continuous time domain into series of discrete intervals. Discrete intervals. I will explain you the situation. This one is not discrete. Discrete. It's like discrete intervals. In this signal varies, where time varies from 0 to 330 milliseconds, we could take a sample every 30 milliseconds, because we will separate sampling in the time. Okay, so just think we have 330 seconds. Okay, we will just what we have to do, we will have to explain the situation. It's like what, we will separate at all places maybe 12 piece area, and or two, so we can generate there 12 sampling area, and it will be like 330 divided 12. It will give us the sampling place and some information values. Let's do it. Okay, let's come up and take this example, maybe all of them. Yes, let's take it down here. Yes, now what we will do again, same, just in this point, where is my yes, this one, let's say for it orange. The point is that here, and also we have the point here. I told you I don't have good example for this point. Again, 3, 4, 5, this point, and here we have 1 and 2. Maybe the last one can be here, 2, and the other one will be here. The first one is 1, the other one will be 2, and last one will be this. Okay, let's do it something like that. Anyway, tag this T to here, it will be good. The V can be here. Okay, I told you I'm sorry for plotting. It is not good, I believe that. Okay, let's go on again. Let's say this point is representing here, this point representing here, this one is here. Oh, point is that here, and here, this one is here, this one is here, it's here, that here, this one is here. Let's do it straight. Let's do it here. Okay, this place, it's just representing the sampling times, okay, sampling intervals. This place, this is our volume of the sound. Anyway, I will show you all of them. Okay, let's come down. Let's say for that, this is the point, I think. Yeah, just where is it? Right here. Yes, let's say for it that that let's look. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think one piece I forget. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's just the also one here. I forget it. Sorry. The other one is here. Yes, here. So we have not there. It's just here. Let's put it here. Yes, this point. This one it's 12. Okay. Let's don't write anything there, and let's say that gives us of samples of the signal between between 0 and 330 milliseconds. Now we can express the signal as the signal as a series of sampled points. Now, what I am saying here, we have 330 seconds, we have 12 samples. Just divide it. How you can do it? This is easy. Let's come down. I will, where is it? Close it. Let's come down again here. Okay, just you have to divide. Okay, then what you will find there, you will find again some solution there. Let's do it together. I was check all information from there. Each point will be our place. Look at that. This, all the way like that. 12 samples in the 330 seconds. We just separated. Now we will check what we need there. Okay. The first point is for 0 is 7 volt. We'll say. I think this one we can change this color to here because I have to say 7 for it. Okay, let's come down and we have here, we can say millisecond, seconds. This place can be volt. Okay. This one, 0. Maybe I can do it with parentheses. It's like 0 representing 7 volt. Let's take this example from here. Let's go inside it and do more. And then we can just do this one is 30. No, this one is 0. This one is 30. And this one will represent or maybe we can do really simple way. It will take lots of time. Just I want to make clear, but we can do here very easy this thing. Can say this one is, let's take it here. Let's do it milliseconds, something like that. Let's say this one is 0 and this one is 7 and this one is 30 and this one will be 5 point and all the way some number and come down. Close also this parenthesis here. The right side is representing volts, left side representing what, representing our milliseconds. This one is 60. Look at that, it's all the time going 30 more, okay? This one is representing minus 71. Point, just put there some number. Because we will speak later about details. And for 90, it will be minus this one. 7. Let's do it some number again. Other one will be 120. 120 will be this one, like that again, and there will be some number. That the other one, let's put in this place. This will be, and this one is just 700. This one is just this. Close it. Let's come down again. 180 will be and some number again. And this one will be this. It will be some number of again this place. This will be 24 and really just put some number there, no matter what. For now, for future it will be important. Okay, let's take them right. Let's do it like that. And the other one will be and 74. Really put some information again. The 300 will be minus 31 and some number again there. Okay, the last one, 100 will represent here 24. Okay, This is our information here. Now I will show you it. I will come up our points here. The first one is representing, the first one is representing 7, I mean 0, representing 7 volts. Let's take this volt there. Maybe let's take them down. Let's do time. Let's give there a little space between them. Was the first one little down. What happening? Crazy computer just come here and really it's all that. Okay, the first one is representing 0 representing 7 volts. The other one 30 representing, I mean this point, sorry, this point this point is 30 representing, so you can think 0 to 330. It's this point is 30, this point 60, 90, 120, 150, and it's all the way going like that. Okay, this one is representing what? Representing 95. Look at that, this place is 95, and the other one 90, it's 90 milliseconds representing there. I think this one is this. Okay, this is 90, this is 60. 60 representing 171, no, 71. This place is minus 71. Okay, and it's all the way going like that. So we can represent milliseconds about volt. What is our intervals here? Okay, let's come here and write again. Let's say the y values are only as size as our computer can store numbers stored in stored in computers aren't infinitely precise and maybe round off. I think you remember this problem, round off problem, just like you're dividing 10 to 3, and it's all the way going like 3.4, and it's going like that, and so later it's coming 3. It's like p numbers. There is no way to stop it. This is just infinity number. It's coming there. We have some round off problem here also. Let's take this round off into blue color. Okay, let's say here the values, no, the inverse let's do it, the inverse of the sampling interval is the again important place, sampling rate. Let's take it again in place. You can do it some color, like maybe to represent it, it can be something like that. This is looking a little different than other color. Sampling rate, and let's write it. Sampling rate, the number, let's do again our 0. No, the color black. It's not, it's black. The number of sampling, I think, samples, the number of samples in a second, in a second or other unit of time for example, a sampling interval of 30 milliseconds, okay, you can think milliseconds, corresponds to a sampling rate of 33.33 samples per second. Now, the inverse of the sampling interval is the sampling rate, okay? The sampling rate we will understand. For example, a sampling interval of 30 millisecond, 30 millisecond, you can think this point to this point. Let's go together. Corresponds to sampling rate of 33.33, like the fast mode here, sampling rate here, okay, 0 to 30, it's speed of your samples per second. According to the Naguist, like that, I think, first shaman, maybe shaman. I will look at it. Sampling theorem. We will look together. Sufficient sampling rate is anything longer than twice the highest frequency in the signal. The frequency, the frequency, I think I wrote wrong. Yeah, frequency, you can think like that. I think I'm not doing wrong yet, right? Say in the signal, the frequency is the signal in the signal. I think I didn't wrong, right? Let's say the frequency is the number of the number of cycles per second and measured in hertz. If, let's put that here, if signal has a maximum frequency frequency of 500 hertz, a sufficient sampling rate is anything greater than yes. Anyway, I will finish it, then I will speak. I will explain it to you all of this kind of situation. We will look at together. A typical sampling rate for music recordings recordings is 48 kilohertz. So it's like 48,000 really samples per second. Per second. Look at that. Right. Let's close it and say that's a little over double the highest frequency that frequency frequency that humans can hear. Humans can hear 20 kilohertz. Really, this is like that. Let's close it and do it. If the audio only contains, if the audio only contains human speech, human speech, as is often the case for phone calls, much smaller sampling rate of 8 hertz, yes, can be used since O hertz is the highest highest is the highest frequency in most speech. Yes. Let's explain the situation. I will be fast, I promise you. Now, The inverse of sampling interval is the sampling rate, okay, between two places. So this point, in this points, just think we have 30, 60, 90, all the way it's going like 30, 30, 30 more. This first 30, I mean sampling intervals, there is also, we have sampling rate. This rate is just for 30 milliseconds is corresponding displays sampling rate. We can put there the 33.33 samples for per second. Okay, now according to the Nyquist Shaman sampling, just look at that here. What is it? Nyquist, yes, Shannon sampling theorem. Look at here. The Narcissist sampling theorem is the theorem in the field of signal processing, which serves a fundamental bridge between continuous time signals to discrete time signals. It is that. Maybe we can look over here also. What does the Nyquist-Shannon theorem state? Nyquist theorem specifies the maximum data rate for noiseless condition, whereas the Shannon theorem specifies the maximum data rate under a noise condition. The Nyquist theorem states that the signal with the bandwidth be completely reconstructed if 2 bit samples per second are used. You can go in this image maybe. Let's check it. Yes, the image is that. Let's go a little inside it. Okay, the point here our place. Let's do it bigger if I can. Yes, we have samplers. This one is samplers. It interpolated curve for represent the place. Anyway, we have the sync function. Have you seen? This one is inside that. And we have, this is our samples in our time, and we have sync function. It is in that, so we have to use this function to solve our things here. What is it? So we can find it step by step. Let's look at their about formula maybe. So okay, you can understand this is our sampling points, okay, and in this point we have some formula to represent our what I said, our sampling rate, okay? So we can do it in this way, like that. So let's come down here. In the signal, the frequency is the number of cycles per second and measured in hertz. If a signal has a maximum frequency of 500 hertz, it's just sufficient sampling rate as anything. Look, as a maximum frequency, I mean, let's come here. If it is maximum, it's like here, frequency is like here, then our, look at that, I will explain it to you. Our maximum frequency, if it is 500 hertz, the our sampling rate is anything greater than 1000, okay, 1000 hertz sampling rate. Please, I'll notice you. So for that, the frequency is here. Just think our frequency is here, and our sampling rate is 1000. It's up bigger than this place. So just I can plot it. Just think our where is it? Our frequency here, and if our frequency is here, like 500, you can think like 500. Let's do it. Our sampling rate is thousand. Okay, this is like that. So this one is hertz. Again, this one is hertz. Okay, you can think like that. I told you, if our frequency is here, this point, then our sampling rate is here, 500 more. If it is 200, it will be 400. So if our frequency is 300, our sampling rate will be 600. If our frequency is 100, our sampling rate will be 200. If the 20, it will be 40. I think you get it. Light it. So we have also formula, but let's speak later about it. For that, we told this example here. So a typical sampling rate for music recordings is 48 kilohertz. It's like 48,000 samples per second. Okay. Sampling rate. It's so you can think kilohertz is also representing samples. Okay. It's just kilohertz and samples. It's just working together. That's little over double the highest frequency that humans. I mean, this is frequency. Okay, this kilohertz. It's like 180,000. We have samples inside it. Now I will show it you what I'm saying. Frequency that humans can hear 20 kilohertz. So if the audio only contains human speech, as is often the case for phone calls, when you speak with the people with your phone, calls a much smaller sampling rate of 8 kilohertz can be used, since 4 kilohertz is the highest frequency, is the most speech. So what we are saying here, just think here, if the frequency of the sounds is 8 kilohertz, our the sampling rate will be there 4 kilohertz. So sorry, if our frequency is 4 kilohertz, it will be our sampling rate will be 8 kilohertz. Okay, so it always will be like that. We are just limited when you speak with the phone. Just some engineer limited it to about sounds. So just think, if there is no limit, then some sounds will come like crazy, and really you can't control it. But engineers is just working with some science men or science people, and they are solving this problem together. How many kilohertz is good for ear? How much will be more like 20 kilohertz? It will be, so it will be lots of, so it's crazy. Okay, the 4 is good for our ear, for the close place, I mean. Okay, the other topic will contain again in another video. It will be a reminder place. Okay, just don't worry about it. This place is you can say, okay, this place will be quantization. Let's speak in another video that.